Log on, tune in, find out. Another good idea from Cambridge.
From CALTECH, and she will tell us about something.
Let me write it down. So we'll talk about a 4d-2d correspondence. For Sicilian gauge theories. Sicilian quivers, I think. Sicilian quivers. This is work that I did last year together with Christoph Keller and Jeroen Swim. Okay, so let me first of all start by introducing this gadget, the Sicilian quivers. So already in this talk this morning, we've seen something about n=2 quiver gauge theories. I will be talking about n=2 quiver gauge theories as well. But about a different class of n=2 gauge theories. So I will restrict myself to SU2. And I will not only talk about linear quivers, as Vasily did this morning, but I will talk about a class of generalized quivers that has been discovered recently by Davide Gaiotto, starting from linear quivers, but using the properties of S-duality that act on those theories. So let me sort of start by an introduction into these generalized quivers. Well, n=2 theories consist of gauge multiplets and vector multiplets. Gauge multi. And the matter is organized in hypermultiplets. And the way I denote these quivers is in terms of a picture, where gauge multiplets are represented by round boxes and hypermultiplets will be represented by square boxes. So for example, if you look at an SU2 gauge theory with 4 hypermultiplets, that's a superconformal quiver, and the corresponding quiver diagram can be drawn in this way. So let me explain this picture in a second. So 4 hypermultiplets transforming in the fundamental representation of SU2. That means that their flavor symmetry will enhance to SO8, and SO8 splits into 4 SU2s, and these are the SU2s that are represented in this diagram. Let's see. So the gauge group, so there is a gauge coupling in the theory, which I will denote by tau UV. So I will emphasize that this is a UV coupling, it's a microscopic gauge coupling. Let's see, and later on I will also use the notation QUV, which is equal to the exponential of tau UV. So S-duality, so this is a superconformal theory, and S-duality will act on this theory by fractional linear, well, oh, sorry, yeah. Transformations on tau uv, but at the same time it will act on this SO8, on this flavor symmetry, and it will act on this SO8 by triality, and that effectively means that some of these SU2 flavor groups that I've illustrated in this picture will be exchanged by S-duality. Well, this is, so what Gayotta realized is that you can use this S-duality to construct more general quivers than we know before by just starting with linear quivers. So let me shortly illustrate that. So for example, if you start with a linear quiver, so I'm not putting in the SU2s anymore, so all of these boxes and circles have SU2s in them. So this is a gauge theory which has 3 SU2 gauge groups. These boxes correspond to bifundamentals that transform under both of these two SU2 gauge groups. And so if I use S-duality, if I look at what S-duality does on this quiver, I can look at all of these nodes separately and use the S-duality action. So I can, for example, look in the limit in which this gauge group is actually weakly coupled and can be roughly seen as 2 flavor groups that are weakly coupled to each other. I can use S-duality then on this, sorry, so I can use S-duality then on this gauge group, and I can use S-duality to exchange this flavor group with this flavor group. If I then look at what the resulting quiver is that I get, I get a quiver of this form, where this one and this node come together in this gauge group. So this is a new kind of quiver, and this interaction, which I will draw completely in this form. This is a new interaction that doesn't couple 2 gauge groups, but it couples 3 gauge groups. So it's a trifundamental interaction, and it's known as a T2 block. So by using S-dualities on any kind of linear quiver and just try to see what kind of quivers you can get, you can see quite easily that these are the only new gauges that you introduce in your gauge theory. So this class of what I call Sicilian quivers these are quivers that are built from this building block, this T2 block. Let's see. So let me denote this trifundamental field as Q ABC, where these ABCs are SU2 indices, so they take values in 1 or 2. This trifundamental field forms a half hypermultiplet representation of the n equals 2 supersymmetry algebra. And it actually has a Lagrangian description. So its Lagrangian description is given by a usual kinetic term. Let me just write it down briefly. So in superfield notation, plus cyclic terms, plus a Yukawa term. Which is of this form. Oh. Plus cyclic permutations. So if you look at higher rank gauge theories, you will get new theories which are called Tn blocks, which don't have a Lagrangian description, but the SU2 theory is kind of special in that all of these quivers have a Lagrangian description, and that will make things easier for us later on. So it's important to realize these half hypermultiplet representations, they're kind of tricky. So in general they will not be CPT invariant. So the field that you're looking at needs to have special properties in order to make it CPT invariant. In particular, it will require that the representation under the gauge group is a pseudo-real representation. So SU2 for, well, so in this case we have a field that transforms under the fundamental of SU2 times SU2 times SU2, and that is indeed a pseudo-real representation. So this trifundamental makes sense. You can conclude, you can include it in your theory, and you get a physical theory. You cannot replace this SU2 by U2, because in that case you get a complex representation, and this half hypermultiplet is not physical. This is also going to be important in our story. So that's the 4D gauge theory part. Let me come to the 2D geometry next. So these SU2 gauge theories, you can embed them into string theory by using M5 rates. And there is a nice correspondence between two-dimensional geometries and four-dimensional quivers. For example, if you would wrap your M5 brane around a four-punctured sphere, which you can draw in this way, this correspondence tells you that on a two-dimensional side, on a four-dimensional side, you will get a gauge theory, which is exactly the one that we discussed before, the SU2 gauge theory with coupled to four hypers. If you would start out, which is an example that we're going to see later, if you would start out with a six-punctured sphere, well, it's not as nice as it could be. You will get a gauge theory which actually includes this T2 block. So again, it's a superconformal theory including this T2 block. So how does this correspondence work? Basically, SU2 gauge groups get replaced by tubes in the Riemann surface, and flavor groups turn into punctures on the Riemann surface. So if you start with any kind of punctured Riemann surface, then a decomposition in pairs of bands will correspond to a particular representation of the gauge theory. I should also say that the UV couplings, the gauge couplings in this theory, will correspond to swing parameters on this side. Of the pairs of bands. So let me shortly since we already know curves that correspond to four-dimensional gauge theories, let me shortly tell you how these well-known Seiberg-Witten curves correspond to this new kind of curves, which are called Gayotto curves. So if we start with a certain four-dimensional gauge n equals 2 gauge theory, we can look at its low energy behavior, and all the low energy behavior is encoded in a Seiberg-Witten curve. Which is usually denoted by sigma. And this Seiberg-Witten curve encodes all the low energy data, so all the IR data of the gauge theory. So that means it encodes the IR couplings, the Coulomb parameters, and the masses. The Seiberg-Witten curve is in fact a branched vibration over this curve that I introduced here, over the Gayotto curve, which we will denote by C. And the degree of the vibration is given by the rank of the gauge group. So in the theories that we will be interested in, this is a 2-to-1 covering. So maybe I should say that this IR coupling is the period matrix of the Seiberg-Witten curve. So this Gayotto curve encodes all the UV data, and in particular, as we saw before, it encodes this UV coupling star UV. So this relation between four-dimensional gauge theories and two-dimensional geometries has been tested in several ways. So for example, by looking at superconformal indices, by looking at BPS states. So what I will focus on today is the relation that is discovered by Alde, Gayotto, and Tachikawa, and they will look at, so we will look at Intelton partition functions of this n equals 2 gauge theory. This is the four-dimensional side. This has been conjectured and tested in several cases to correspond to conformal blocks on this chaotic curve C. So the new thing that we will do, so before, so this has been tested for these linear quivers or cyclic quivers that correspond to either genus 0 or genus 1 Riemann surfaces. What we want to do is we want to extend this to these Sicilian quivers, to these generalized quivers. So in particular, we want to compute the instanton partition function corresponding to this T2 block. Because that is the elementary building block of these generalized quiver theories. So, this morning we've already seen a very nice introduction into this instanton calculus. And so in this talk I will basically use the same tools. Let me just briefly give you an overview of that again. So this instanton partition function, it will depend on the UV couplings of the theory, and it will depend on the Coulomb parameters and the masses, and it will localize to an integral over, so it will localize, to a sum over instantons and so these instanton sectors, they contribute with a factor which is given by an integral over the instanton moduli space. Which is the ADHM moduli space, and what we integrate, so the form that we use to integrate this over is some Euler character of a certain bundle, and this bundle V encodes the matter that is the matter that is part of the theory. So this V encodes solutions of the Dirac equation. In the instanton background. So in order to be able to compute this theory, we need to introduce, or one way to do this is to introduce this omega background, which I will denote by R4 epsilon 1 epsilon 2. And what this does is it regularizes the instantons, so it prevents them from moving out to infinity. And the end result will be a partition function that will depend on all of these parameters, but also on this epsilon 1 and epsilon 2. And it will basically, so its first contribution, as Vasily said, will be 1 over epsilon 1 epsilon 2 times the prepotential of the n equals 2 theory, and it will have some higher order contributions that have an interpretation in terms of gravitational corrections to that to the theory. So the IR couplings of the gauge theory are encoded in the second derivative of this prepotential, which will depend on all of these parameters. So what Vasily did this morning is he looked at linear quivers for U and I gauge groups. In this talk we want to look at generalized quivers. So instead we want to look at generalized quivers. Which involve this half hypermultiplet. So that means we cannot just use Insulton calculus for the UN gauge groups. We really need to find some new tools to look at SU2 Insulton calculus. So what had been done previously, mostly, is just consider Insulton calculus for a group U2, and then at the end specialize to SU2 by setting Coulomb parameters to these SU2 values. But this is not possible if you look at if you want to treat the SU2 half hypermultiplet. So this is well, when thinking about this, there is one obvious other thing you might do. You might look at other gauge groups. For example, if you consider Insulton counting for SPN gauge groups, you can easily see that SP1 is in fact equal to SU2. So instead of looking at Insulton computations for UN gauge theories, you could just as well start considering Insulton counting for SP1 gauge theories. So Insulton counting for other ADE gauge groups basically works the same as for unitary gauge groups, except that instead of looking at the ADGM data for unitary gauge groups, you need to look at the ADGM data for ADE, for general SP or SO gauge groups. Let's see, so so Insulton counting for example, gauge group SP1 had been done before by Nekrasov and Shachin. That is, they wrote down the formalism, but they hadn't actually computed too many partition functions. So what we started doing is we started looking at Insulton counting for this gauge group SP1, and then we discovered some kind of funny things. So. Let's take an example. For example, this gauge theory with 4 flavors. Instead of representing it in this way, you could equally, from a gauge theoretic perspective, look at an SP1 gauge theory and consider it in the SP1 formalism, where the flavor symmetries are given by SO4 groups. So we started computing this Insulton partition function in the SP1 formalism, and we tried to compare this to the Insulton formalism for the U2 gauge group. And then we discovered that these two quantities actually do not at all agree on the nose. So this worried us a little, but then after a while we discovered that actually something nice is going on, because if you express, so remember that these Q's are the UV couplings. Instead, if you express everything in terms of if you instead express everything in terms of IR couplings, which are the physical quantities, you will see that there is in fact an agreement between these two. So interval counting for these SP1 theories actually does make sense. But what does it mean? What does the fact mean that if you express it in terms of UV couplings, that they don't agree? So we played a little bit around with this, and we figured out that in the end that you can make them agree in terms of if you impose that these two objects if you impose that these two objects are the same, but you introduce two different UV couplings, you will find that they are actually equal if these couplings are related in the following way. So what is going on here? It actually turns out that this has a very nice geometrical interpretation. So remember that the chaotic curves that correspond to the n equals 2 gauge theories, they can be found by embedding them in M theory in terms of M5 range. And if you look at the embedding of SP1 gauge theories into M theory, you will notice that the chaotic curve for the SP1 theory is actually not just a 4-punctured sphere. Instead, the chaotic curve for the SP1 theory will have a branch cut that is running between two of the punctures, whereas the one for the U2 theory doesn't have that branch cut. And in fact, you can find out that there is that the chaotic curve for the U2 theory is a double cover over that of the SP1 theory. Now, as I told before, these chaotic curves encode the UV gauge couplings, and in this case the UV gauge coupling is the cross ratio of the punctures. So if we parameterize the punctures here in this way, then these punctures are at the following positions, and you can easily see that if you compute the cross ratio of this curve now in terms of so the cross ratio of this curve is related to Q squared, so that's the SP1 UV coupling constant, whereas the cross ratio of this curve in terms of Q is given by the following expression. So if you compare these two guys, then you notice that they are actually almost the same up to a factor of 4. So that means that this relation that you find purely by doing instanton counting in the 4-dimensional theory actually knows about its theoretical embedding. So it knows about Gayotto curves. Which is kind of neat. Okay, so this is only about linear quivers. So let me continue with the relation to conformal blocks. So these instanton partition functions, they know about Gayotto curves, but even more is true. You can compare this complete instanton partition function to a certain conformal block. On this Gayotto curve C. For instance, if you look at the gauge theory coupled to four hypers, which corresponds to this 4-punctured Riemann sphere, then what you need to do is you need to insert vertex operators in the Virasor algebra, and you can find that this instanton partition function for the U2 theory agrees with a conformal block on the Gayotto curve. So I should say that these vertex operators, they encode the masses of the hypermultiplets. And what this is a projector onto a representation that is characterized by the Coulomb parameter of this gauge theory. Moreover, the central charge of this Virasor algebra is encoded in terms of these parameters epsilon 1 and epsilon 2. Which this instanton partition function depends on. So we've just seen that if you look at the SP1 theory, the instanton partition function is different, and in fact you can also compute a corresponding object on this side. So remember that the Gayotto curve in this case is a 4-punctured sphere with a branch cut. And what you can do in fact is look at an extended version of the Virasor algebra, so what is called a W2,2 algebra. I don't want to, well, okay, let me just say this. So you can compare this instanton partition function for the SP1 theory to a chiral block for a W2,2 algebra. So this means that it's an algebra which has two W currents which have degree 2, and you also find an agreement on the nodes. But that is not what I want to focus on in this talk. Let me continue. Let's see. Because I want to reach the generalized quivers, so let me make one extra remark about this correspondence. So if we want to consider, so far we've considered superconformal theories and compared them their instanton partition functions to conformal blocks on the corresponding chaotic curve, we can also consider asymptotically free theories. And in that case, the correspondence just works by decoupling some of these hypers, so we can send their masses to infinity. And for example, if you want to look at pure SU2 gauge theory, we find that its partition function, its instanton partition function, can be written in terms of certain states. As a norm of a certain state, where this is an eigenstate of the L1 operator mode in the Virasor algebra with eigenvalue lambda. So lambda is the scale of the n equals 2 theory. Okay, so these are all the ingredients I need to go to what the goal of this talk was. So the goal of this talk was to look at T2 blocks and to consider the 4d-2d correspondence for these blocks. So maybe I should stress that in this correspondence between instanton partition functions and conformal blocks, these flavor groups, they correspond to insertions of primary vertex operators, whereas the gauge groups correspond to insertions of descendant fields. And that makes it natural to conjecture that if you consider this T2 block, that its partition function, or its CFT block, can be should be written in the following form. So it should be just a correlation function of 3 vertex operators. So I will explain this notation. So what this gadget means is a vertex operator which includes all descendants of a corresponding primary field, and its conformal weight. So the descendants are encoded in this partition I1, I2, and I3, and the conformal weight of the corresponding primary is related to these Coulomb parameters A1, A2, A3 of these gauge groups. Well, if you think a little bit about this, it's actually not so trivial that this is the case, because this conformal block is in fact not symmetric under the exchange of punctures. Whereas if you would compute an instanton partition function for such a block, it would be symmetric under the exchange of the punctures. So it's not immediately clear that this is indeed the right answer. So interestingly, so since this is on itself is not a superconformal field theory, it's an asymptotically free theory, we can start instead with this six-punctured sphere, the theory that corresponds to a six-punctured sphere, which has the following quiver. So we can compute the conformal block using this ingredient for this quiver and take the limit in which we send all of these masses, m1 up to m6, to infinity. And then what we see is that we get an object which can be represented, oh, I just removed it, in terms of these states that we saw before for the pure SU2 theory. So what happens is that the partition function, if we decouple all of these hypers, the partition function can be written in terms of these states that we saw before. H3. So So what we need to do is we need to turn one of these states into a vertex operator and then compute this 3-point function. And it actually turns out that, this has some really nice features. So this is obviously symmetric under the exchange of punctures. So we basically conjecture that this block is the instanton equals the instanton partition function for let me say it in this way so that we have this agreement that the instanton partition function for this T2 block is given by this conformal block. So how do we test this thing? Well, as we saw before, we cannot use the U2 instanton calculus. What we can do instead is look at the SP1 calculus. So we can instead consider a linear quiver that consists of two gauge groups, so the SP1 gauge group and the SO4 gauge group, which are coupled by a bifundamental, because this gauge theory, as a gauge theory, is equivalent to this T2 block, since SO4 splits as SU2 times SU2. And indeed, if you compute the instanton partition function corresponding to this quiver, you will find agreement with this conformal block. Is there a question? So let's see. Okay. So let me summarize. Let me summarize by giving some open problems. So in general, we would like to let's see. So in general, we would like to look at instanton partition functions for higher genus curves, Gaussian curves. These instanton partition functions, from the gauge theory perspective, they will involve all these UV couplings. From the conformal field theory perspective, these UV couplings correspond to certain choices, choice of coordinates on the complex structure moduli space. And since the instanton partition function just chooses one particular choice of coordinates, that means that if you want to compute the conformal block corresponding to such a quiver, you need to have the right choice of coordinates. You need to fix the right choice of coordinates. So if you express all these quantities in IR quantities, they are supposed to agree whichever choice of coordinates you take on this complex moduli space. However, if you want to find an exact agreement in terms of UV coupling constants, you need to pick the right choice of coordinates. And it is still unclear for us what those coordinates, how those coordinates are characterized. So an open question is, so what are the coordinates that fix this identity between instanton partition functions and conformal blocks for higher genus Riemann surfaces. So I think I'll end there.
Questions?
Sorry, probably you mentioned you explained one further, but I missed the comment. Why did you consider U2 instead of SU2 and to see the correspondence between SB1 and SB1 is osmotic to SU2, right?
Yes. So maybe I should say it in a little bit more detail. So if you embed SP1 theories into string theory, you do that by using D4's NS5 branes and O4 planes as well.
Okay.
So in that sense, SP1 is a different choice than SU2. It doesn't matter in terms of IR data, but it does matter in terms of UV data, whether you choose the embedding in terms of SP1 groups or in terms of SU2 groups.
Okay. Could you can you explicitly write that what's the operator PH5 in the middle of the component?
Yes, so it's a projector. I'm not sure whether I can. It's something like the inverse of the cut matrix and a complete set of. So these are all the descendants of this primary field phi that has weight related to the Coulomb parameter. Yeah, so that's a symbol for all.
That is equal to instant partition function of U2.
Yes. Yeah, so there is a corresponding correlation function in terms of this W2,2 algebra that gives you the instanton partition function for the SP1 theory.
Okay, so if the U2 Guyotto cover is double cover of the ST1.
Yes.
Then how about is there any relation between?
Yes, so the Seibert-Witten curves are actually equivalent.
Equivalent?
Yes,
okay.
because they contain the IR data, and in the IR,
I see.
these
Oh,
two
that's why.
theories are equivalent. Yes.
Okay, thank you very much.
Yeah. Just small question: is that factor of 4 anyway relevant to that you mentioned?
No, I don't think, well, I don't know whether, I mean, I don't know any relevance of it. Yeah, I think it's just a factor. Yeah. Yeah. Well, it's just a scaling, well, yeah.
Okay, if there are no more questions, let's just thank Lotte again.